Okay, how's the volume? Good. So today we're going to see something very cool. So you've got a lot of time to digest it over this long weekend, along with your turkey. But I'm going to need assistance from one of you. Somebody with a cell phone or a laptop. There's none of those in here, right? Go to Google and type, search for flip a coin. Good. Do you have a little thing that lets you flip a coin? I don't want it. I will need you to, or I will need those of you who want to engage in this to call out coin tosses for me. So we're going to talk about something called Skiplists. These are a beautiful data structure that, as far as, basic fundamental data structures go, are fairly young. So now they're older than some of you, but that's still fairly young in this world. And so they go back to 1991. They use, you can do a few things with them. We'll talk about how you can use them to implement the sorted set interface, and as well how you can implement the list interface. And they fit in well now right after we've looked at linked lists. So skip lists are in some way a kind of linked list. So let's see if we can define them here. I hope this is not going to take too long. All right, let's put something in here that we can put an order on. Let's say 3, 7, 9, 10. Okay. So to make a skip list, you start, one way to think of it is you start with a list that you already have. And I will, let's pretend that this is a singly linked list. And from that, so that list we will call L0. And we saw last class that it's nice to have dummy nodes. Sometimes that simplifies things, and that's going to be the case here. And we'll create a dummy node that we'll call the sentinel. Anybody know what sentinel means? It's this kind of thing that watches over everybody. So the sentinel will watch over the elements of this skip list. All right, so now I need a coin tosser. What we do is we're going to walk through this base list, and from L0 we're going to make a list L1, and we're going to do that by tossing a coin for each element in L0, and if that coin comes up heads, this thing will get promoted into L1. If it comes up tails, it will only stay in L0. Okay? So first coin toss. Heads. So 3 gets promoted. Second coin toss. 7 gets promoted. Third coin toss. Coin toss. Okay. Coin toss. Coin toss. Okay. Coin toss. Coin toss. And a coin toss. Tails. Okay. So that gives us a new list, L1. And since L1 is not empty, the sentinel will take part in that list as well. So we didn't toss a coin for the Sentinel, but for everyone else we did. All right. What do you think we do next? What's that? Yeah. So from L1, we're going to make a list L2, and we're going to do that by tossing a coin for each element in L1 to see if it makes it up into L2. If it comes up heads, then it will be in L2. If it comes up tails, then it'll stop being promoted there. All right. So someone toss me a coin. Heads. Again. 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 And again. So now we have L2. And we keep going to make L3. Coin toss. Tails. Coin toss. Coin toss. So L3 looks like this. And we keep going to make L4. Coin toss. And that's L4. And we keep going to make L5. Coin toss. Good. All right. And L5 is empty, so we stop there. Anything, if we repeat this, nothing else is going to happen. Okay? So the Sentinel lives up in L0 through L4, and then L5 is the first empty one. Okay? So that's what a skip list looks like. Okay? Next thing, well, so what can we do with a skip list? Well, you can do a lot of things, but fundamental to all of them is what's called the search path. For a value x, and x is in the list L0. And it works like this. You start at the top of the Sentinel. So we start up here. And we apply the following rule. If we can go right without reaching or overshooting x, then we go right. Otherwise, we go down. So we just repeat this thing repeatedly, okay? So we start at the top, here, and let's take our x to be, I don't know, 21. No, let's take our x to be 16. It's maybe a bit more interesting. So, From here, if we go right, do we reach 16 or overshoot it? We overshoot it. So that would be too far. So we can't go right, so we'll go down. So the search path proceeds down one step. From here, do we go right or go down? It's the same thing. We would overshoot 16 if we went to the right, so we go down. From here, do we go right or do we go down? We go to the right, because we can step to the right to 3. That doesn't overshoot 16 or reach it. So now, do we go right or down? Down. We don't want to reach 16. So we go down. Now, right or down? Right. From 7, we can still go right. From 9, if we go to the right, we will reach 16. We don't actually want to do that, so we go down. From 9 in this list, we can go right. And then finally, from 10 in this list, if we go right, we'll reach 16. So we go down, ending the search path there. Okay? So the search path for 16 takes, includes 3 nodes in the Sentinel, 2 nodes with the value 3, 1 node with the value 7, 2 with the value 9, and 1 with the value 10, and it stops just before reaching 16. Remember, in a singly linked list, if you wanted to do something to this node, this is really the node you want to be standing at to do something. Once you're at this node, you can't, for example, remove it or anything because you have to change this pointer. So this is the right place to stop. All right. So it's clear the way the search path works. Okay. So that's the definition of the search path. And I will write down the main theorem that's used to drive everything in Skiplists. And that's about this search path. For any value of x, the expected length of the search path x is at most 2 times log base 2 of n plus a constant. Okay? So it doesn't matter which node I'm asking about. So there's a few things here that will be new to you. Some of you maybe. Some of you are learning about these even now. So one of these things is expected length. So this term expected, how many of you have encountered this before? Expected value, expectation, average, mean, all of those things mean the same thing. So somehow this is an average. So there's a fixed x here, but there's an average that we're talking about. So what is it that we're averaging over? Yeah. So, when I say here's the elements in your skip list by telling you the values in L0, that doesn't really tell you what the skip list looks like. For that, to know that, you need to know what happened with those coin tosses. And so when we talk about the average, we're talking about the average over all of the possible skip lists that you could build by tossing coins over what's in this bottom list. Okay? So we are averaging over this is the average over all skip lists built by these coin tosses. So that's the random part of this whole experiment, is the coin tosses. That's why we have this expected length rather than just saying the length. Okay? And I think it's clear that you could not say that for any value of x, the length is always at most 2 log n, because I can give you an example where that's not true. Start with this list, toss n tails in a row, and all you have is this list. Now, if I take x equals 42, the only way to get to it is to walk through this entire list. And the number of elements in this list is 1, 2, 3, 4, 5, 6, 7, 8, 9. So the length of the search path there is actually 9. And the log base 2 of 9, well, there's an O of 1. That's going to be bigger than the logarithm of n. So n is 9 in this case. Okay. So it's not something you can guarantee that happens all the time, because it's always possible that you got really unlucky with your coin tosses, but it's true on average. Okay. So you see, actually, one thing that while we were making these coin tosses, which the thing about random coin flips and randomness in general is it doesn't look like what you expect. So you get these weird, these things that kind of annoyed us while we were making this or stood out, like, you know, that our first 3 coin tosses came up heads, and that this guy 24 rose all the way up to here. But neither of those things are bad in some sense. So a coin toss coming up heads is not bad, and a coin toss coming up tails is not bad for these search paths, because, well, stuff that comes up into these higher lists means we get a chance to make bigger jumps sometimes in our searches, and stuff that stops appearing in these lists are things that we get to jump over. And this theorem captures that intuition. And we'll prove this theorem, not right now, but first we'll look at the applications and why this is so useful. But and we'll prove it maybe at the end of the class or maybe at next class. Okay. Just a couple of notes. How familiar are you guys with these logarithms? So if n is 1,000,000, then what's log n, roughly? Not 1,000.
6.
Nope, wrong log. Wrong base.
20.
Yes, it's about 20. So log base 2 of n is actually less than 20. And that's because 2 to the 20 is bigger than 1,000,000. Okay. So then 2 log base 2 of n, this is, in this particular case, is 40. And this constant here, actually, when we analyze it, we'll see that it's actually less than or equal to 2. And so if I have a skip list that contains 1,000,000 elements, so more than I would be able to draw on this board, and I ask how long is the search path for a particular element in that list, well, its expected length is not more than 42. Okay. So 1,000,000 things, I can get to any one of them in about 42 steps. So that's impressive, right? I mean, that's much better than half a million steps, which you would get if we only had the one list and we had to scan through it looking for one of these things. All right. So applications. The first one, well, actually before that, one thing I'll point out, you can think about this for a few seconds. The search path, we defined it by starting at the sentinel and going right whenever we could until we fell off the bottom. There's another way to think of it. You can start at the node in the bottom list, so the one that comes just before 16 in this case, and whenever you can go up, you go up, and if you can't go up, you go left. You get exactly the same search path. Here I can't go up, so I go left. Here I can go up, but I can't go up anymore, so then I go left. Here I can't go up, so I go left. I go up, can't go up anymore, so I go left, up, up, up. That'll give you exactly the same path in the reverse direction. All right. So if you want to implement a sorted set, in the book, this is called the S-set interface. In Java, it's called sorted set. There's basically three things you want to do. You want to be able to find some value x. You want to be able to add some value x to the set, and you want to be able to remove some value x from the set. And find here means something very specific. So you want to find the smallest value in the set that is greater than or equal to x. All right. So let's see if we can use a skip list to do that. So let's say I want to find 23. In this particular list. How would you do it? Well, first of all, what should the answer be? So 23 is not in this list, but according to this definition of find, what should the answer be? 24. So the smallest value that is greater than or equal to 23 in this set is 24. Okay. So it's very deep down in this list. How are we going to find it? Not a trick question. Yeah. Let's see if we can follow the search path for 24 without really knowing what 24 is, just using our value 23. So I start here. Now, should I go right? So I don't know. Maybe 23 is in this list, maybe something 23.5, 23.1. I don't know anything yet. So if I'm standing here, I'm looking for 23. Should I move to the right or go down? Down. If I go to the right, that's going to be too far. Here, it's the same situation. If I look to the right, I see something that's bigger than 23, so I go down. Here, if I look to the right, I see 3. Should I go right or down? Right. Here, if I look to the right, I see 16. Should I go right or down? Here, if I look to the right, I'm in the situation I was in before. I see 24. That's bigger than the 23 I'm looking for, so I should go down. Here, I again see 24, so I should go down. But from here, I see 21, which is smaller than 23, so I should go to the right. And then from here, I see 24, so I would go down again, but I'm out of the list at that point. And so what do I conclude from this? I conclude that 23 comes after this last value in the search path and before this next value, the one that comes after it. Okay. So the answer to my find in that case is just the successor of this node in the search path, so the 24 that's there. Is that clear? Okay, and is that going to be fast or not? So let's say that I had 1 million numbers in this list. How much work did I have to do? On average, I had to take 42 steps to find that thing. That's pretty good for looking through a list with 1 million numbers, right? So, so this find operation, well, what does it do? It does some comparisons with things on the search path. It does some pointer jumping, but basically it follows this search path. Each step in the search path only takes constant time to, do a comparison and go right or go down. And so this takes O of log n expected time. Just because the length of the search path is O of log n. Okay. Any questions so far? All right. How about if I want to do the next operation, which is to add an element to the skip list? So let's say I want to add, I don't know, let's do 35, say. So I want to add 35 into this list. How would you do that? No, maybe not 35. Let's add 12. So where would 12 go? Yeah. Yeah. So let's look at the search path for 12, which we actually already have here because 12. And we can follow that search path and that'll bring us to here. Now what? Yep. Okay. So we want to add this thing here. So that means we're going to insert it into this singly linked list, L0. And so we do that. That's not a problem. We saw that you just create a new node. We have a pointer to the thing that comes before it in the list, so we can set its pointer to that. And before that, we set this guy's pointer to 16. So it's in there. That's not a problem. Anything else? So now we do some coin tossing. So somebody want to toss some coins for me? At least one head, though. Heads, good. Next. Heads, so it's going to get promoted up into L2. Next coin toss.
Tails.
Tails. So it's only going to go up to L2. So somehow in this process, we have to not only insert this thing in L0, but also insert it in L1 and L2. So which nodes do we need for that? 3, 9, and 10. 3, 9, and 10. Is there anything that distinguishes those nodes in terms of the search path we just followed? They're all the places, or they're all places where the search went down. And it went down because if it had gone right, it would have overshot the thing that we're looking for, which means that the thing we're looking for should come right after that in that list, right? So here's the clean way to do this. You follow the search path. While you're doing this, you have a little array which has, in this case, 5 slots in it. And while you're following the search path, in that array, you keep the pointers to the nodes where the search path went down. So in that array, you would have this thing, this thing, this thing, this thing, and this thing. Now we did, in fact, we would, yeah, and even 10. So now we did our coin tosses, and we realized that we're going to promote this thing up into 3 lists, L0, L1, and L2. And the things, the locations, the nodes that we need to update for that are actually just the 3 elements, the first or last, depending on how you order the array, the 3 elements that are in this array of nodes that I kept on the search path. Okay. So I look in that array, I see that it contains, at the position 0, it contains 10, so I use that to insert it there. That array at position 1 contains 9, so I use that to insert it there. And at position 2, it contains this node 3, so I use that to insert it there. Okay. And if you look carefully at the definition for set, if we tried to add it and it was already there, then we shouldn't do anything. Well, we still have that option now, right? We get to there, we find it, we say, okay, we're not really going to add it, it's already here. Okay, good. So now, 2 things we need to, or one thing we need to convince ourselves of first is, well, let's think about edge cases. Is there anything weird that can happen when we do this process? Yeah. That it wants to go past. Yeah. So if we toss coins, we may get into a situation where we get 1, 2, 3, 4, 5 coin tosses in a row that come up heads, in which case we would want to be inserting this thing all the way up into L5, so in a list that's not even there. And if that happens, well, then you create a new thing on top of the sentinel. That thing points to your newly created node, and you're fine. Right? So you just promote it all the way up. Just make sure the sentinel is high enough for it. So that's one edge case. Anything else? In fact, an edge case that comes up when searching in the search path. For example, if we were to search for 35, there's something kind of weird that happens you have to look out for. So a search for 35 would go start here, it would walk over to 24, and now you're not really comparing 35 to the next thing on the right because there's nothing on the right. If there's nothing beyond this, then you just go down. Okay? So you'll end up, I mean, that works. Just don't try and blindly compare to whatever value is stored on at the next position, because there may not be a value there. First check for null. Okay, so that's, you know, some corner cases in the code you have to worry about. But more fundamentally, this theorem for about the expected length of the search path is about a skip list. And a skip list is defined as something that I get when I start with all my elements in the bottom list, and I toss coins to see if they make it into L1, and then I toss coins again to see if those make it into L2, and I toss coins again to see if those make it into L3. Now, this new list that I have wasn't made exactly like that. Maybe this first list was made like this, but then I added this new value 12, and I mean, it came later. That's not the same thing necessarily. So we have to convince ourselves that this list that I get after adding 12, you can't tell the difference between that and a list that I just started with all the values in the bottom and tossed coins this way. Is there any reason that it would be different? So who thinks that something weird happened here? That I need to, that maybe this list is different than a skip list built the other way? Nobody? Yes? Yeah, it changes some of the path, and so, I mean, it changes something. So I guess the question is, I mean, formally you're asking, is the distribution over lists made this way, is that different from if I started with all the elements in the bottom list and tossed coins? And the answer is no. And that's because all of these coin tosses are independent. They don't rely on each other. So if we did them in a different order, it doesn't change anything. So for example, you know, I said we start at this bottom list and we toss a coin, and that tells for 3, and that tells us if it goes up into L1, and we toss a coin for 7, that tells us if it goes up. So that's one way to do it. Alternatively, we could have started at 3 and just kept tossing coins, heads, 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 until we get the first tails, and say, good, that's where 3 goes. Would be the same thing, right? I mean, whether we toss all those coins first or whether we, you know, come back and toss them again later, that's not going to change the distribution of these things in any way. So it doesn't matter that 12 showed up later and we tossed its coins later. It looks just like it showed up. It was there from the beginning. Okay, good. All right. So that's how you add. And now what if you want to remove something? Let's say I would like to remove, well, I find 24 kind of annoying, so, well, maybe not 24. Yeah, no, 24 is kind of annoying, so let's remove it. So how would that work? Where do I start? Yeah. Yeah, let's follow the search path to 24. That's actually this red path that I've drawn here. And now I need to take 24 out of these lists. And so let's see. Needs to come out of, this thing needs to be adjusted. This pointer needs to be adjusted. This one doesn't. This one does, and this one does. Anything stand out about those in terms of the search path for 24? Yep.
Where it went down?
It's exactly the places where the search path went down. So to delete something, if I want to, for example, remove 24, I just follow the search path, and there's, when you go down in the search path, it's because something to the right is bigger than or equal to the thing you're looking for. So at this point, the thing to the right is equal to the thing I'm looking for, and that's my clue. So that's my clue that I should just remove it at this point. So top down, I start here, I look to the right, I see the thing that I'm trying to remove. So I cut this link and move down to the next node. Here to the right, I see this thing that I'm trying to remove. So I cut this link and down to the next node. Here to the right, I actually take a step to the right, I take a step to the right, I take a step to the right, and again I see the thing that I'm trying to remove. So I cut that link and move down. Here again I see the thing I'm trying to remove. So I cut that link and move down. Here I take a step to the right. Here again I see the thing I'm trying to remove. So I cut that link and move down. Yep.
You said that it goes down every time that what it points to is equal to or greater than what it's looking for?
Yep.
Correct?
Yes.
Okay, so if at the top level, if that directly pointed to like 32, let's say,
Yes.
instead of 24,
Yep.
do you have destroyed that pointer?
So you're asking if the picture looked like this and 32 was all the way up here, then here I would look to the right and see 32. So that's bigger than or equal to 24, so I would go down. But it's not equal to 24, so I wouldn't cut the link to it. Okay. So it's just when you look to the right, I mean, you'll always go down if the thing is bigger than or equal to what you're looking for. And if it happens to be equal to, then it's time to splice it out of the list. Okay. Super simple. This is just a few lines of code to implement. And again, how long does that take? Well, it's all proportional to the length of the search path. So all of these operations run in O of log n expected time. Okay. If you've never seen, go look at the code for sorted set in the Java collections framework, or tree set rather. So, exercise for those of you interested. Look at tree set, the code for that in the Java collections framework versus Skiplists. Skiplists, I think it's called S set, in the book. Or look at the source code that accompanies the book. This thing is a nightmare, really complicated, and we'll learn it's because it's using a red-black tree. And this is super simple. Each function, add, remove, find, it's just a few lines of code. Okay. All right, so that's one thing you can do. And let's write that down over here. With a skip list, we can implement the sset interface so that add, remove, and find each take O of log n expected time. Okay, good. So that's a bit surprising. So this structure has list in its name, but it implements the sorted set interface. Yep.
Forms to remove, you also remove sentinels if they are not pointed
Yeah, that's true. That's the other edge case. And in fact, it applies here. I forgot about it. So the picture looked like this. There was L4. And so L4 and L3 actually no longer point to anything. So you remove them. In reality, what happens is each node gets implemented using a structure that looks like this. It has a data item X and the pointers for the lists that it belongs to. So that includes the sentinel, whose data item is not used. But when you remove something from it, all you're doing is, changing a variable that says the height of this skip list is now only 2 as opposed to the 4 that it used to be. So it's an easy operation. Okay, so what about implementing the list interface? So remember, list interface, basically there's get and set, and there's add and remove. And, somehow we saw that if you use arrays, you can do get and set in constant time. But if these add and remove operations get expensive, and usually there's something like, if you use a double-ended, some kind of circular array implementation, then you get something like the min of I and n minus I. So again, if n is 1,000,000, this thing could be as big as 500,000. It would be nice to get that down somehow. And so this is all using arrays. And if you use linked lists, well, then it gets worse in some sense. If you use linked lists, then get and set, they're the ones that also take a lot of time. Let's say in a doubly linked list, that's the kind of time you're looking at. And add and remove, well, the hard part about adding and removing from a linked list is just getting to the place the node that you need to add and remove. So you have to traverse the list to find it. But once you found it, it was easy to add and remove. And so, we could, I'll put an O of 1 here with a little footnote that says with a pointer to the node I want to remove. Without the pointer, you're still stuck with the problem of finding that node. So somehow, you have, on one side, you have linked lists where you could add and remove things very quickly in constant time if you knew where they were. With arrays, you can get to things in constant time. That's great. But adding and removing is slow, and then in linked lists, getting to the thing you want is slow. And so what's the trade-off here? Can we find some trade-off? Well, the answer is you can use skip lists and do all of these operations in logarithmic time. And let's see how we would do that. This is getting too messy, so I'll have to redraw it. So I want to use a skip list to implement a list. I'm not going to do actual coin tosses this time. Don't forget the sentinel. Oops. Okay, so here's a skip list that contains some elements in the bottom. So just think of those as elements that are stored in a list. They're not necessarily in sorted order. See, there's an X here that's somehow out of place. And we're supposed to be thinking of these things as this is the element at position 0 in the list, at position 1 in the list, at position 2 in the list, and so on. So rather than searching for these things by their value, we want to be able to search for them by their index. So here's the trick. So what should the index of the sentinel be? If we have to think of it, what's the natural number to put here? -1. Okay? And let's think of these edges in our skip list as being assigned lengths. That the length tells us from what index, what's the difference in indices between the two endpoints of this edge. So if I go from -1 to 0, that's a difference of 1, 1. So in the bottom list, all these differences are 1. But at the next list, they change. So for example, the difference here is 2. Here the difference is 2. Here it's only 1. Here it's only 1. And here it's only 1. Here the difference is 3. Here the difference is also 3. And here the difference is 6. Clear? All right. So I need to be able to get to the ith value in the bottom list, the one with index I in the bottom list. So let's do this by example. And let's take I equal to equal to 5. This is where I want to get to. Of course, I don't have a pointer directly to it, so someone says get the 5th element in this list. I want to get there. So here I am. I'll start up here. Now, should I go right or down? I'm looking for the search path for that element at index 5. Down. So I should go down. So somehow, from the information in this picture, just looking locally at what you can see from here, I should be able to decide that I can go down. So right now, I'm at some position index k. It's the index of the sentinel. So it's -1. Okay? Now from here I can cross an edge whose length is 6. So what index will that take me to? I'm trying to get to I equals 5. I can cross an edge whose length is 6. I'm at index minus 1, so what index is at the other end of that edge? Yeah, 5, right? Because k plus 6, in this case, is equal to 5. Now that is bigger than or equal to I, the value I'm looking for. So that tells me that the thing to the right is too far. This would either reach the thing I'm looking for or overshoot it, so the search path should go down. So the search path goes down. Okay. Now, I'm still at the node with index minus 1 and searching for I equals 5. So now what? From here, I see an edge whose length is 3. So what index will that lead me to? 2. So k plus 3 is equal to 2. And that is smaller than 5, smaller than I, which is 5. So that tells me I should take this turn to the right. And the value of k has changed now. Now I'm standing at a node whose index is 2. And now I just repeat the same question again. From here, with this new value of k plus, if I take a step to the right, it's on an edge of length 3. It's 5. That is bigger than or equal to I, so I should go down. Smaller than 5, smaller than I, so I take a step to the right, and I update the value of k by subtracting, by adding 2. So now k equals 4. And I repeat. From here, k plus 1 is 5. That's bigger than or equal to 5, so I go down. Here, k plus 1 is 5. That's bigger than or equal to 5, so I go down. So this process will take me to the last node in that search path will be the node that comes just before the index that I want. So I just return the value in the successor of that node. Okay. And so this is just a skip list, except now each edge is augmented with an extra integer that tells you its length, how many elements it jumps over. Of course, the natural place to keep that is just along here with this node. Right? You have a next pointer and a pointer that tells you how long that, an integer that tells you how long that is. So that's good. So I think now get and set are easy. You just follow the search path. That takes you to the node in L0 that precedes your node, and you either return the value stored in the next node or you change the value stored in the next node. And so that will take O of log n time. Now how about if we want to add something? So let's say I want to add something at position, well, let's say I want to add something at position 4. So where does that go in this list? It goes between the 3 and the 4, right? 4 comes right after 3, so the new thing that I'm going to add is going to be here. So I can follow the search path for 4. That will take me to this thing. And that will also, that's what I want, right? Because I want to splice this thing into this list here. That's exactly where I want to be. But then I'll have to toss some coins for this thing to decide how high up it should go. That's no problem. We've seen how to do that before. So, we would first, in this case, we can first toss the coins, decide how high it's going to go, then we follow the search path, and when the path turns down because it's overshooting the thing we want at a level that's lower than the height we're supposed to start inserting at, then we splice it in. That's easy. So in this case, it's a bit simpler than adding in a set because we don't have to worry about not adding a duplicate value. So, we follow this search path. We'll first decide that the height of this thing will be 3, so it's supposed to live in the lists 0, 1, and 2. We decide that by tossing coins. And you take the usual algorithm, or this algorithm I just described for following the search path. But when it goes down and you're at level less than or equal to 2, then you splice it in, like this. Is there anything else we need to worry about? Yeah. Yeah. So all of this working relies on the edges having lengths associated with them. So when we splice this new node in here, that's going to change those lengths of some of those edges. So how do we deal with that? So in the search algorithm, when we're following the search path, we're keeping track of the index of the node that we're at, right? That's the way we did it. We kept this, k was keeping track of the index of the node that we're at. So for example, right at this point, we knew that k was equal to 2. This node has index 2 in the bottom list. Now, the node that we're inserting, we know what its index is going to be in the bottom list. It's going to be equal to 4. Right? So this guy is going to get 4 in the bottom list. All of these will have to get increased. Though we don't store them explicitly, they're implicitly getting increased. So we're at node 2. We're splicing in a node which is going to be at position 4. So what's the length of this edge? 2. So this edge is easy to update. It's a 2. Okay? And we know that there's this 4 here. What about this? So this used to be a 3. We should keep track of that. What about this edge? What's its length? 3 minus 2 plus 1. So this edge used to be of length 3 because it represents 3 edges in the bottom list. We're adding a new node underneath this edge. So actually this edge, if it jumped over all this, would be an edge of length 4. Right? So 3 plus 1 is 4. But, so we can think of this edge here would have been of length 3 plus 1 equals 4. But we split it into 2. Into this part and this part. This part we know how to calculate. It's just the difference between k and I. That's where we got the 2. So this part must be whatever's left over. That's the 4 minus the 2 is 2. So in general, it's basically this number, 3 minus 2 plus 1. Plus 1 is because we added a new node in the bottom list. The minus 2 is because part of this edge length got assigned to this part. Whatever's left gets assigned to this part. Okay. So you can insert into one of these things and keep the edge lengths updated, which means next time you can do searches again. Okay. All right. And yes, good point. In fact, every time you turn down, every time your search path turns down, that increases the length of this edge by 1. Okay. So this becomes a 7. And in fact, if you write your code carefully, then some of these things fold together, right? So you decide you're going to go down, you increase the length of this edge by 1, and then either you go down, or in this case, before you go down, you splice this thing in. Increasing the length of this edge by 1 accounts for the plus 1 in this formula. So you can streamline things that way. Okay? Any questions? It's all clear? And so then the only thing left to do is to implement remove. So let's, for example, remove 2. That means we want to remove this thing. So we follow its search path. Its search path looks like this. And on the way down, we should be removing it every time we see it. Okay? So, here, well, we should be doing a few things. So here we're standing at position -1. We see an edge of length 7, so that takes us to position 6. That's too far, so we know that we should go down. Anything we should do before we go down? Yeah, we're going to delete something underneath this edge, which means that its length is going to decrease by 1. So we decrease its length to 6, and down we go. Now we move from index -1. No, we don't. From index -1, we add 3. We see that the thing we're looking for is to the right. So -1 plus 3 is 2, which is bigger than or equal to 2. And since it's equal to 2, that means we should be removing this thing. So we have to splice this thing out of the list by changing this pointer to point to there. That's no problem. What is the length of the resulting edge? Yeah. -1, yeah. So the length of the resulting edge is 3 plus 2 and -1 because we're taking one thing out of here. Or if you like, the first thing you do is subtract, because you're going down, you subtract 1 from the length of this edge, and then it's just the sum of the two edge lengths. Right? Just like we subtracted 1 from the length of this edge. So these two join together. The 3 plus 2 minus 1 becomes an edge of length 4, and that effectively slices this thing out of here. And now again, here we move to index 0. We look to the right. We see 0 plus 2 is equal to 2, so we're both going to go down. We're going to splice this out. We're going to fix up the edge length, so we subtract 1 from here. That gives us 1 to account for the thing we're splicing out. We replace these two edges with a single edge whose length is the sum of these two, so that's 3. And then we move down to the right. And the same rule applies here. We can subtract 1, we get 0. We splice this out, replace it with a single edge, which is the sum of these two things. So we're left with an edge of length 1. It's all very clean. Implementing it is, delicate, but the code is beautiful once it's done. It's just very, very short and simple. What's that? Which index values? Oh, yeah, but these are not things you actually store. I just wrote them on the board so that we don't forget what the indices are. These are all, if you had to change all those, you'd be out in trouble because there's, n minus I of them you need to change. So they're all implicitly stored by all of these lengths that you keep in this list. All right. Any questions? Good. So now I can implement over here, write down again, using a skip list, we can implement the list interface so that add IX, remove I, get I, and set. Looking at an application where you need to be adding and removing things in a list and in a list, and those adds and removes are not in easy to predict places, so they're not near the ends or near the middle necessarily, but all over the place. Then this is a much better alternative to than either a linked list or an array-based list for this thing, right? 1 million elements, you can add and remove anything in about 42 steps. That's better than what you get with any of the other structures. All right, good. Here's a warm-up exercise for what we're going to do next class. We're going to prove that theorem about the length of the expected length of the search path. But first thing I would like to, ask you to think about is what's the expected length of the list Li? So the list L0, L1, L2, L3, L4. So here's an easy one. And I don't include, so this is excluding the sentinel. I won't count the sentinel. So what's the expected length of L0? Yeah. That'll be true, but L0 doesn't have an Li minus 1, so we have to start somewhere. Is there anything about this that's random?
The base case, L0 is always n.
Yeah, so this length of L0 is not even a random variable, it's just n. Okay. And what's the expected length of L1? N over 2. And why is that? Yeah, so somehow each element in L0 appears in L1 with probability 1/2. And so if we add those up, we expect that there's n elements in L0, we expect that to work out to n over 2. Now, what about L2? I think all of you know the answer, unless you've really not been paying attention. But what's the reason? N over 4. So somebody give me some informal justification for that. Yeah.
Well, you can only continue on with the ones that you already have from L1, and you're going to have approximately half of those, and so
Okay.
divide
So
that by 2, you get an L4.
okay. That's a perfect example, I'm not making fun of you, of the reasoning that I want to avoid here. So I don't want to have to argue because although it's possible, it would be an incredibly difficult computation to argue about the size of L2 as a function of the size of L1. I don't want to do that. Yeah. So how does, there's one thing we know, that L0, it's not even an expectation, just the size of L0 is just n. Yep. Should be n over 2 to the I. Yeah. And that's because, for example, to make it to L2, just look at one guy here. How does he make it to L2? He makes it to L2 because he tosses a coin and it comes up heads. And then he tosses a coin again and it comes up heads. So that's a half times a half. That's a quarter. So the probability that he makes it to L2 is a quarter. And that happens independently for all of these n guys in L0. So you get to n over 4. Okay. And that's the kind of, we'll formalize that a little bit more next class. But that's the kind of reasoning that you can get a correct and simple proof from. Arguing about L2 as a function of the size of L1, or in general Li as a function of size of Li minus 1, that's really difficult or incorrect depending on how you do it.